All right, so this is the continuation of section 8.3. This is on inverse trig functions. So let's find the exact value. This is the sine of, not multiplied by, this is the sine of the inverse sine of root 2 over 2. Now, you might remember from earlier in this section that we said that the sine and the inverse sine will undo each other and give you the exact same answer if a certain condition is met. So let me flip back here. So it was back here where we said the sine of the inverse sine of x is x only when x is between -1 and 1. Well, root 2 over 2, what does that end up being? Is that between -1 and 1? Let's see, shall we? So let's do root 2. Oops, that's not it. Root 2 divided by 2. That gives me about 0.707. Okay, so that is between -1 and 1. So essentially, these two, you can kind of think of it as canceling. You know, kind of like a square root and a squared, right? These two functions undo each other, and you get root 2 over 2. Only because this argument is between -1 and 1. If it was outside of that, there would be no solution because the sine function doesn't go outside of -1 to 1. All right. So let me get back over here. Let's do one with the cosine. How about we put the inverse first? The inverse cosine of the cosine of pi over 3. All right. This one looks very similar, right? Looks like the same thing. Looks like these are going to cancel and kind of undo each other. And they will. That's because this is in that domain restriction for the inverse cosine function. Remember all those domain restrictions that we talked about for the trig functions? The cosine, the inverse cosine's domain restriction was 0 to pi. Because this is between there, boop, boop, easy peasy. Okay, so what happens when it's not? All right, well, what's the inverse cosine of the cosine of -pi over 3? All right, this is not between 0 and pi. So that's not in that interval from 0 to pi. That means we cannot just zip -pi over 3 and we're done. No, 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 no. So what do we have to do? We're going to start on the inside and work our way out. First of all, what's the cosine of -pi over 3? So we're going to need to figure out what that is. So let's just try to look at this kind of as a separate problem. Well, the cosine -pi over 3, let's see, what is that? That's the cosine of, what, -60 degrees? Just in case you're better with degrees. If you want to use some quadrant stuff, you can. You can use the unit circle at this point. Doesn't really matter. That's in quadrant 4 down here. Remember this business? That means this is going to be the same as positive cosine 60 degrees. Because -60 degrees is in quadrant 4, the cosine function is positive in that quadrant, and it has a reference angle of 60 degrees. And the cosine of 60 degrees, hopefully you got this one memorized, and you don't have to go look this up on the unit circle. The cosine of 60 degrees is 1/2. So that means that this stuff right here is 1/2. All right, so we have the inverse cosine of 1/2. All that stuff right there just simplified to be a nice little 1/2. this is asking you, remember this inverse, this is asking you what angle, this is an angle, all right, I'm going to put an equal sign here. What angle between 0 and pi has a cosine value of 1/2, positive 1/2? Well, we know it's going to be a 60-degree reference angle. It's got to be in quadrant 1. It can't be in quadrant 2 because the cosine is negative in quadrant 2. So it's got to be in quadrant 1. So it's got to be a 60-degree reference angle in quadrant 1, which is just a 60-degree angle. You can also use your calculator to help you with this. Let me dig out my calculator real quick. So let's put this in degree mode. Okay, cool. If we want to do the inverse cosine of 1/2, we get 60. It's in degree mode, so we know that's 60 degrees. Okay. If you did, so that's our final answer. I should go ahead and say that. If you did this problem from the beginning, you did the inverse cosine of the cosine of negative pi over 3. I got it in degree mode, so I'm going to do negative 60. So the inverse cosine of the cosine of negative pi over 3 in degrees, boom, 60 degrees. So I just wanted to show you how that worked out. So you might be inclined to just cancel those, sort of, just undo those and just say, oh, it's just going to be that. No, not the case. That is the case when those restrictions are met. All right. So to the notes that I'm going to scan for you guys, we have this stuff. So remember that the inverse cosine of the cosine of theta is only equal to theta when you're in that domain restriction. And then the sine business, remember the domain restriction for the sine function was negative pi over 2 to pi over 2. Just keeping that in mind. That's just reminding you of those domain restrictions here. Okay, so let's find the exact value of the sine of the inverse cosine of 1/4. Now, you're probably thinking, cool, I'll just use my calculator. The sine of the inverse cosine of 1/4, easy peasy, right? So it must just be this 0.96824. I'll just write out all the decimal places and that'll be exact. No. No, it will not. The exact value is going to be the one that has the irrational number to it, so it's not going to be a decimal approximation. All right, so here's what we got to do. Remember that the inverse trig function, the inverse is an angle, right? So keep that in mind. That's an angle. The cosine, the inverse cosine here, its domain restriction is quadrants 1 and 2. It's 0 to pi. Quadrant 1, the cosine's positive. Quadrant 2, the cosine's negative. This is a positive 1/4, so it's going to be in quadrant 1. Okay, so that's just kind of a little side note. That's why I did that in red. Now, let's come back to the blue part, the angle part. Because this is an angle, I called it a Greek letter theta. Okay, so I said let theta equal this. Now here's what I'm going to do. I'm going to use this to build a right triangle using the right triangle trigonometry stuff. So if theta is the inverse cosine of 1/4, I can then take the cosine of both sides that will, eliminate that inverse. So I get cosine theta equals 1/4. And remember, cosine is adjacent over hypotenuse. Because we're in quadrant 1, I'm not going to bother drawing the triangle in a quadrant. I'm just going to draw just a right triangle. There's angle theta. The cosine is 1/4, so that's adjacent over hypotenuse. All right. That leaves me to find this distance right here. From the Pythagorean Theorem, I got a squared plus b squared is r squared. So I end up with b being plus or minus root 15. It's in quadrant 1, so I know it's going to be a positive root 15. Now, look at all this stuff that's in blue. I called all of that angle theta. So, coming back to the beginning, I have sine of angle theta. Now I've got a triangle to go with this angle. The sine is the opposite over hypotenuse. Opposite over hypotenuse. So, opposite over hypotenuse. So it's root 15 over 4. That's the exact value. If you write me out a decimal, no matter how many decimal places you take it, it is still an approximation. So there was a lot of stuff that happened in here, okay? We had to think about the quadrants, the domain restrictions for the cosine function. We had to build a triangle from what was given, the Pythagorean theorem, right triangle trigonometry. There was a lot happening in this little problem. All right. All right, cool. Moving on along. Let's do another one. It's like that. All right, so we've got the tangent of the inverse cosine of negative 1/3. All right, let's start off same things as last time. The red stuff. The inverse cosine, its domain restriction is quadrants 1 and 2, 0 to pi. Quadrant 1, the cosine function is positive. Quadrant 2, the cosine function is negative. Because that's a negative, my triangle is going to be in quadrant 2. All right, so this angle is going to fall into quadrant 2. Keep that in mind. So now I'm going to, again, let theta equal this. I'm going to take the cosine of both sides to get rid of the inverse cosine. So I get cosine theta equals negative 1/3. It's the adjacent over the hypotenuse. This time, though, I'm going to draw it in its appropriate quadrant. Okay, so I got it over here in quadrant 2. That's going to be important. My angle is always made with the x-axis. The cosine being negative 1/3. The negative 1 is because this is one unit going to the left. And the 3 we know is always positive. So now I'm going to use the Pythagorean theorem of this a squared plus b squared is r squared. So I end up getting that b squared is plus or minus the square root of 8, or 2 root 2. I chose the plus because in quadrant 2, those y values are positive. If this were in quadrant 3, it would have been a negative. So it's important to notice the quadrants because that's going to control some of your signs, your plus minus. This is here. All right, I've got this triangle built. So now I'm going to come back up here, tangent of theta. Tangent theta is opposite over adjacent. All right, so opposite, 2 root 2, adjacent, negative 1. So if I do 2 root 2 divided by negative 1, I get negative 2 root 2. This is the exact value. Remember that decimal is not the exact value no matter how many decimal places you write out. Moving on. Let's do another one of these because I know these can be kind of tricky. All right, you guys know what to do by now. This inverse sine, its domain restriction is quadrants 1 and 4. It's from pi over 2 to negative, or negative pi over 2 to pi over 2. So it's either quadrant 1 or quadrant 4. The sine function is positive in 1, negative in 4. Because that's a negative, we're going to be in quadrant 4. If we let theta equal this stuff, and what I did here was I skipped the step of taking the sine of both sides. Because I know that every single time I'm going to take the sine of both sides, essentially I'm moving this to the other side and getting rid of the inverse. So I get sine theta is negative 1/2, sine's opposite over hypotenuse. It's in quadrant 4. So here's my angle down here in quadrant 4. This is -1/2. So it's opposite over hypotenuse. I know the hypotenuse is positive. So I know that that negative has to go on that 1. And that's the case, right? Because this is going down. This y direction is going down. So of course that's going to be negative. This x direction is going to the right. So it's positive. So when I use the Pythagorean theorem and I get x squared equals 3, x is plus or minus √3. So I'm going to choose the positive because the x's are positive over here in quadrant 4. All right, and you know how to wrap it up. It's going to be secant of theta. The secant of theta is 1 over cosine. That's a reciprocal function. Cosine is adjacent over hypotenuse, so secant is going to be hypotenuse over adjacent. All right, so hypotenuse over adjacent. So that's going to be 2 over √3. I'm going to rationalize that to get rid of the radical in the denominator, and we get 2 √3 over 3. Okay. Let's do something different. And by different, I mean about some word problems. Oops. Sorry about all the rustling here. A building that is 21 meters tall casts a shadow 25 meters long. Find the angle of elevation of the sun to the nearest degree. All right, let me draw you a picture of what's going on here. So we got the sun. We have this building. It's 21 meters tall. Remember, a meter is about a yard. And then the shadow is about 25 meters long. The angle of elevation of the sun means the sun must be over here so that the shadow is going this way. That makes sense, right? The sun's over here, that's casting the shadow in that direction. This is the angle of elevation of the sun, this angle over here. All right, because it's kind of like if that shadow is on the ground looking up to the sun. So there's my right triangle. So I want you to find the angle of elevation to the nearest degree. Well, if I'm looking for this angle and I have the opposite and the adjacent, what trig function stands out to you? I mean, technically you could use any of the trig functions. You would just have to use the Pythagorean theorem to find this, but let's just pretend that we don't want to find this, because I don't. So what trig function is going to involve the opposite and the adjacent? Well, it's the tangent, or the cotangent. I just grabbed tangent first. Okay, so that means that the tangent is 21 over 25. So how do you solve that for theta? Well, if this were, let's say this were theta squared equals this, you would take the square root of both sides, because that's the inverse of a squared. So you have to do the inverse tangent of both sides. All right? That's what you have to do. You can, please, you cannot do this. Please. Oh, for the love of everything that is good and holy. Please don't do this. And tell me theta is 21 over 25 divided by the word tan. Oh, Lord, that's so bad. Okay, if you had the square root of x equals 16, would you divide both sides by that radical? No, you wouldn't, because that's trash. And you're not trash. So, how do you get rid of this? Well, this isn't, first of all, this is not multiplication. That's the tangent of theta. So you need the inverse of that function. The inverse tangent. So just like I can take like the sine of both sides, I can square both sides of an equation. Get this, I can take the inverse tangent of both sides. In doing so, the inverse tangent of this tangent, those go away, and I'm just left with theta. Here I'm left to find the inverse tangent of 21 over 25. This is going to be an approximation. So I'm in degree mode. Make sure you are in degree mode for this. And that's 21 over 25. And I get about 40 degrees. If you're in radian mode, it's going to give you the radian answer, which is fine. But I don't know about you, I'm much more comfortable looking at degrees than radians, especially radians in decimal form. Those, I'm not as keen on looking at those and knowing what those look like to know if my answer is reasonable. Okay, last one. A security camera is mounted on a wall 9 feet above the floor. What angle of depression should be used if the camera is to be directed to a spot 6 feet above the floor and 12 feet from the wall? Probably going to see the whole problem here. I mislabeled this because I can't count, but that's okay. Y'all love me anyway. All right, so let me draw you a picture of what's going on here. So we've got a wall. 9 feet above the floor is my little camera. All right. It is pointed to a spot that is 6 feet off the floor. And it's 12 feet from the wall. Right? So this spot is 12 feet this way and 6 feet that way. So 6 feet above the floor, 12 feet from the wall where the camera is. So that's what I'm looking at. This 3 up here is just the rest of that 9. I'm just going to go out on a limb and assume that these walls are, parallel, and this is not some security camera mounted in some, busted room. All right, so you can see this up here is also 12, and we got that right angle. So look at that pretty little right triangle. Now, how did I know to use this angle right here? Well, first it says it's an angle of depression. So we know it's an angle that's looking down. So this camera, its horizontal is straight ahead. Right? So there's its line of sight. If it's going to have to rotate down to look at this spot, there's the depression angle right there. Okay? So I got this 3, there's my angle of depression, and I have 12. So I have the opposite and the adjacent once more. All right, so let's break out the tangent again. Tangent of theta is 3 over 12. If I take the inverse tangent of both sides of this equation, once again, I'm taking the inverse tangent of 3 over 12. If you want to reduce that to 1/4, you totally can. It won't change your answer. And it's not always the inverse tangent for these, but... All right, so I get about 14 degrees. Alrighty, so that finishes us up. Sorry for all the chaos there. That finishes up for section 8.3.